Well, good evening, ladies and gentlemen. And no, I didn't bring any props. I got you to bring the props. Um, since its discovery in the late 1790s, I don't think any other metal has managed to capture the public's imagination quite like titanium. It has an unmatched reputation for quality and durability. And I'm willing to bet that quite a number of you own a titanium pen, a titanium wedding ring, a set of titanium golf clubs, maybe a titanium body part. I'm not going to ask you to put up your hands. Titanium has been featured in song titles. It's been featured in books, in movies, and there's even a Marvel superhero called Titanium Man. And there you can see Titanium Man. I think this slide says it all. You can see Titanium Man happily bashing Iron Man into the concrete. So that pretty much sums up my whole presentation. Now, this reputation is not undeserved. Titanium has an almost unique combination of properties that makes it useful in a wide range of applications. It is as strong as steel, but only half the weight. And that makes it very useful in aerospace applications where they're always trying to reduce weight. It is compatible with human bone. So it features, or it's used in many implants, both dental and medical implants, hip replacements and knee replacements, and so on. It has an exceptional corrosion resistance. So from an engineering point of view, we find it useful in things like pressure vessels, pipelines, tanks, heat exchangers, where we can use titanium's corrosion resistance to expose it to very harmful chemical process streams. And not to forget the consumer products. Bicycle frames, fishing tackle, jewelry, where we take advantage of the low density of titanium, the high strength, but also the beautiful, lustrous, white, silvery color. All of these products have one thing in common, and that is that the titanium metal has to be shaped or formed to form these products. And that is where titanium loses its luster to a certain extent. It is more difficult to form titanium than many other competing engineering metals like steel or aluminium. If we look at the conventional processes used to shape titanium, casting is one where we melt the titanium in a furnace, cast the molten titanium into a mold, and then the titanium solidifies to assume the shape of the mold cavity. Now, titanium is very reactive to the atmosphere, so all of this has to be done in vacuum, which makes it more difficult to successfully cast titanium. A method that's very popular in the engineering industry is to take big pieces of titanium, usually formed as cast ingots or hot forged products, and then to machine away all the titanium that we don't want. So that is a subtractive process, and it ends up in a lot of waste. A more elegant process to form titanium is to use additive manufacturing, where instead of removing the metal we don't want, we build up a titanium component layer by layer. And the process that I think most of you may be familiar with is powder-based additive manufacture, where we use an electron beam or a laser to selectively melt a bed of titanium powder to build up a component layer by layer. It's a wonderful method for producing very complex three-dimensional shapes. The surface finish is excellent, the tolerances are very good, but it is a painstakingly slow process. So it works very well for producing complex small parts, but not that well if we want to produce big components for engineering applications. Another variation is to use a process called wire-based additive manufacturing, where we use a conventional welding process, feed a titanium wire, melt the titanium wire, and then build up a component using welding. And this is what it looks like. So you can see the welding torch over there, and we're depositing layers of titanium metal. This process is much better for producing big components. It's much faster. You deposit a lot more metal in a short time. But the dimensional tolerances are not as good as the powder-based additive manufacturing process. And the component needs a lot more machining after it's been produced. What all of these processes have in common is that we have to supply heat at some stage during the manufacturing process, and often a lot of heat. And that affects the metal in many ways. And as material scientists, what we're really interested in is how the process affects the metal on a microscopic level. And often what happens on a very small scale affects the properties in a really big way. And what I'm going to focus on today is something we call the grain structure. When you look at metals, all metals are composed of a three-dimensional network of grains. And those grains are not that different from the soap bubbles you see when you take your foam bath or wash the dishes at night, just on a much smaller scale. As material scientists, we want those grains to be as small as possible. Unfortunately, this grain structure usually develops during the solidification stage of the material. So once we melt it and it re-solidifies to form solid, the grain structure is formed. And once it's there, it's very difficult to refine it, almost impossible. Unfortunately, as things go, we can't refine it easily, but it's very easy to get the grains to grow. And from a metallurgical point of view, that is what we don't want. We want the grains as small as possible. Now, the easiest way to get those grains to grow, which is what we don't want, is to apply heat. The moment we apply heat, the grains start growing. The bigger grains start consuming the smaller grains, which is, by the way, exactly what happens in soap bubbles. So when you lie back in your foam bath tonight, just take a look at how the bubbles behave, and you'll see that the bigger ones tend to eat up the smaller ones. So the moment we apply heat, the grains start growing, and that has a very detrimental effect on the mechanical properties. The strength goes down, the ductility and the formability is reduced, and the toughness, the impact toughness of the material is also reduced. This has an impact on our manufacturing processes. This is a typical example of a titanium weld. So you can see the weld in there. And those white lines are the boundaries between the individual grains. If you can look at the scale bar there, that is 1 millimeter. You can see that the grains are quite big, almost on the scale of your soap bubbles. And that is exactly what we don't want. We want those grains to literally be microscopically small. But the heat we supply during the welding process, and the same applies for casting, allows those grains to grow almost uncontrolled. So what we're proposing, and this is our big idea for tonight, is a way to minimize the grain size of titanium. Titanium is notoriously difficult to grain refine. It doesn't follow the same rules as many other materials. So we propose a two-pronged approach where we add compounds during the manufacturing process, whether it's casting, welding, or an additive manufacturing process. First of all, to manipulate the grain structure of the material, or the solidification behavior of the material, so that as the material solidifies from the liquid state, you form more grains that end up being smaller, and at the same time also preventing grain growth as the material cools down after solidification. And we can do that with the same compound added to the material before it solidifies. The idea is to go from a grain structure that looks something like this, coarse, elongated grains, to a small, fine equiax grain structure that will give us much better mechanical properties. So the big idea is that when it comes to titanium and metals and alloys in general, unlike rest of life in general, smaller is better. Thank you.